Hi everyone, this is the video lesson for 4.4 Concavity and Points of Inflection Part 1. Let's take a look at the warm-up. Number 1, what are inflection points? So mathematically speaking, to find the points of inflection or inflection points, you have to find the second derivative of the function f of x and set this to 0. Or you find the second derivative, f double prime of x, and you want to find out the x values, which will make this undefined. And again, some students think about this as undefined, others look at it as does not exist. Either one is fine. So this usually happens when you have a fraction and you're looking at the denominator, and those points that makes it 0 may be a vertical asymptote, sometimes they're actual inflection points, and again we'll demonstrate this in some of the examples. Now, in terms of what an inflection point looks like, here are two examples. So again, in the first case, notice how the function has a maximum, also a minimum, and in the second case, you have a minimum followed by a maximum, and of course, the idea looks something like this. When you scan from left to right, notice how the slope of the tangent is decreasing. Then it hits the point, which is called the point of inflection, POI, point of inflection or inflection point. And after this point, as you continue to look at the slope of the tangent, the slope is now going to increase. So this change from increasing to decreasing or decreasing to increasing, that's called the inflection point. So likewise, if you look at the second case, the slope of the tangent is increasing, then it hits the point of inflection. As you continue, the slope of the tangent starts to decrease. Again, that's not the only case of an inflection point, but I'm just sharing with you some of the basics, and we'll investigate this a little bit more in the examples. Number 2, when is the function concave up? This is really important. The ultimate goal is to figure out the 4 cases when you have the intersection of concave up and concave down, increasing and decreasing. This is coming up in a moment. But in terms of concave up on its own, the function could look something like this, or something like that, or something like that. So these are the 3 cases of when a function is concave up. And of course, mathematically, you find the second derivative of the function, f double prime, and you make this positive. On the other hand, number 3, when is the function concave down? This is the exact opposite. Concave down could look something like that, or just the left-hand side or the right-hand side. These 3 cases, again, are examples of a function when it's concave down. And the second derivative is going to be negative. So one thing you should notice, if you've been doing all your homework, is the parallel between increasing, decreasing, and concave up and concave down is in essence the same idea, right? And you can kind of see the parallels. So one thing I do want to add for you is the fact that how can we find out the maximum or the minimum using concavity? This is also known as the second derivative test, which we'll get to in number 5. But even just by looking at this, the hint is if it's concave up, it's going to be a minimum. And if it's concave down, it's going to be a maximum. So we're going to write this down officially once we get to number 5. Now, number 4. How do we calculate the interval of concavity? I just wrote it. I wrote it again. If it's concave up, the second derivative is positive. And for concave down, the second derivative must be negative. Number 5, what is the second derivative test? So again, if you haven't learned the first derivative test, go back to the previous video or the previous lesson of 4.3 or 4.2 or even 4.1 just to get the continuum, which we'll cover there. But a faster approach is really just to figure out the second derivative to see if the critical point is a max or a min. So all you do is this. If you take the second derivative and you plug in the critical point, And again, critical points are the points you find when you set f prime to be 0 and you solve for x, or you look at all the points that would make f prime undefined. Sometimes they're vertical asymptotes, sometimes they're actual points. So once you find those critical points, which we call C, and you plug it into f double prime and it's positive, this implies that this point is going to be a minimum. And again, we know this because if it's concave up, which looks something like that, then this point at the bottom, it's a minimum. On the other hand, if we find the f double prime of C is going to be negative, this means it's going to be concaving down, which means the point, the critical point, is going to be a maximum. And again, it looks something like that. So, just to recap, before I keep going, here's a table of the different cases. And I want to merge this in a moment, right? That is probably the most important thing. So, if you kind of take a step back and say, okay, what have I learned so far in terms of increasing, decreasing, and concavity? So this is the previous lesson. And again, you can go back and watch them if you like. Interval of increase looks like that, or like that. The interval of decrease looks like that, or like that, or like that. And now we kind of think about the current lesson, which is concavity, specifically when it's concave up and concave down. So we know it's concave up when it's like that, or just like that, or like that. And concave down is the exact opposite. So I'm introducing this idea, which is really a preview. I'll just write down as new. If you can understand this now, you are ahead of the game. You're ready for the rest of this chapter when we put all this together and you do this under one graph. So again, this is brand new, and just open your mind to this and you're going to be okay. So think about the top, increasing, decreasing. Think about concavity, concave up and concave down. This is the summary of everything from the two graphs or the two tables from above. If you think about a graph that is increasing and concave up, it has to be like that. Likewise, if it's concave up but it's decreasing, it's going to be like that. Now, what about increasing, concave down? It's going to be like this. Last but not least, if it's decreasing and concave down, it's going to look something like that. Now, for some of you, you're going to look at this and say, whoa, too much. I don't get it. Well, it's not that you don't get it, it's you don't get it yet. In case you're thinking, I want to get this, what can I do? Here's an idea that you can follow if you like. Write it out once a day, right? Write it out or write it down once a day. So if you do this, you would know this way faster than you would expect. Now, I'm moving on. Example number 1, determine any points of inflection on the graph y equal to x to the power of 3. So again, you're given the function y equal to x to the power of 3. When you find the derivative, y prime is going to be 3x squared. When you find the second derivative, that's going to be 6 times x. And again, what happens is you can find the inflection point or the point of inflection by setting the second derivative to 0. So 0 equals to 6x, which means when you solve for x, x is going to be 0. Again, form that habit just like we did when we did critical points. Don't stop when you find the x value. Find the actual location. Find a coordinate for the point of inflection. When you plug 0 back in, and I'm talking about the original function, 0 to the power of 3 is going to be 0, so the point of inflection is going to be 0, 0. And again, that's all they're really asking in example 1, but I do want to show you a graph just to kind of justify what is going on. And again, in the warm-up, I've given you some examples of an inflection point, and now I'm adding a little bit more to the basics. You know this. I know you know this. You've graphed y equal to x to the 3 from grade 9, 10, or grade 11 math for sure. So in this case, we're saying, okay, there's a point, 0, 0, and that is the point of inflection. Example number 2. This is from page 203 of your textbook, example 4. Determine any points of inflection on the graph of f of x equal to 1 over x squared plus 3. Here we go. Again, very doable. A lot of the basic steps that we talked about, we're going to reactivate here. Now again, personally, when I find the derivative, I would use the chain rule because it's faster. But I know from experience, a lot of you immediately would jump to the quotient rule. Why? Because it's a fraction. And even though I did mention you don't use the quotient rule because there's no x at the top, I know most of you will. So I'm going to be flexible and think about it from your perspective. 6 steps. When you go through the quotient rule, you square the bottom, copy the bottom to the top, you multiply by the derivative of 1, which will become 0, minus, second last step, you copy the top, and the final step, you multiply by the derivative of the bottom. So all we have so far is y prime equals to negative 2x divided by x squared plus 3 quantity squared. And again, the reason is because this first term is going to be 0. Let's keep going. Now we're going to find the second derivative. Let me start it from here and I'll continue in the next column. In this case, you will practice the quotient rule. So you square the bottom, x squared plus 3 squared to the power of 2, that becomes 4. Step 2, you copy the bottom to the top, x squared plus 3 quantity squared times the derivative of the top, which is negative 2, minus, you copy the top, negative 2x, and you multiply by the derivative of the bottom. Again, notice we're applying the chain rule inside the quotient rule. So you take 2 times x squared plus 3 to the power of 1. Don't forget the internal derivative, which is 2x. And again, before we find the points of inflection, you can take out a common factor of x squared plus 3 from here, and also at the bottom. Now, I'm going to continue here. Your goal is to find a point of inflection. So you're going to set this to 0. Notice how when there's a fraction equal to 0, your focus is at the top. And we'll come back to the bottom in a moment just to show you that there's nothing there that's important, but we'll verify that in a moment. So now I'm going to look at the top, I'm going to expand this and collect like terms. So negative 2 times x squared is negative 2x squared. Negative 2 times 3 is going to be negative 6. If you take negative 1 times negative 2x times 2 times 2x, that's positive 8 times x squared. So again, if you simplify this, 0 equals to 6 x squared minus 6. At this point, you can bring negative 6 to the other side. The opposite of multiplying by 6 is to divide by 6. And when you find the opposite of squaring something, that is the square root. Be mindful, there are 2 answers, plus and minus 1, just like that. Again, really, really important. You form the habit of finding the actual location, not just the x component. So I'm going to give you the trust that you can take the calculator and plug it back in. I'm still going to do it mentally so you can see the mental math. If you plug 1 and negative 1 back in, for 1, it's going to be 1 divided by 1 squared plus 3, which is 1 over 4. And if you plug in negative 1, it's going to be the same thing. Because the function is even, if you look at it, it's an even function. Now, notice I didn't forget the denominator. I still want to check this because sometimes all the values that make f double prime undefined, they could be an inflection point. But in this case, I'm trying to tell you that x squared plus 3, the whole thing cubed cannot be 0. So the goal is, are there any restrictions for x? If yes, they may be vertical asymptotes or they may be actual inflection points. And if you take the cube root of both sides, you get x squared plus 3 cannot be 0. And when you bring it over, you would discover that this is not possible. There are no solutions to this. So there are no points in the denominator that you have to focus on. The only inflection points are 1, 1/4, and negative 1, 1/4.